In this video, I want to just really go through one big example. So I'm going to write down the problem, and then it would be really great if you would hit pause, work through it, and then as usual, when you're done, hit play again to check your answer. So essentially, we're going to be given the following reduction potentials. And our first one, I'm going to have tin 2 plus, so I should say our reduction half reactions also, plus 2 electrons, right? Again, we're adding electrons to it, right? It's gaining electrons, so these are reductions going to tin solid. And then my standard cell potential for this is a negative 0.14 volts. And then our second one, I'm going to have chromium 3 plus 3 electrons going to chromium solid, and then its standard reduction potential is a negative 0.74 volts. And what we're going to do is we're going to determine which reaction takes place at the anode and then also at the cathode. So essentially, which is our oxidation, which is going to be our reduction. We're going to write the overall balanced equation. We're going to write the shorthand notation. We're going to calculate the cell potential. So standard cell potential. Not done yet. We're also going to calculate our free energy change. And then one more, finally done, we're going to draw the galvanic cell. So our little sketch where you show the two beakers and the electrodes, flow of electrons, all of that. Alrighty, so please try this on your own, and then when you're ready, hit play and you can check your answers. All right, so hopefully you did that. So we want to determine which reaction takes place at the anode. So remember, that's going to be our oxidation half reaction, and then our cathode is going to be our reduction half reaction. And we know that we want the reduction half reaction to have the more positive cell potential, or half cell potential. So we want it to have the bigger number. So if I go up and look at these two, this one is larger, right? They're negative values. So a negative 0.14 is a bigger number than the negative 0.74, right? We could say it's more positive. We want the more positive one to be our reduction. So this is going to be my reduction. This one we're going to have to reverse when we do our balanced equation, and it's going to become the oxidation once we reverse that. Right, we'll have to reverse this then, and it'll become a positive 0.74 volts. Remember, if we're going to have a spontaneous reaction, since I'm saying galvanic cell, we know we want our reaction to be spontaneous. When I add these numbers together, it needs to come out to be positive. If you would have switched the sign on the wrong one, right, if you would have chose this one to be your reduction, so negative 0.74, and then chose this to be your oxidation, it would become a positive 0.14. And when you added those two together, you would have a negative cell potential. And that's how you would know that you were incorrect, right? To be a spontaneous reaction, which is what we need for a galvanic cell, we need to have a positive cell potential, a negative free energy change, but a positive cell potential. So which one occurs at the anode, that's our oxidation. Let's actually write our answers here. So our answer to A, our anode, I am going to reverse that one when I write it here. So I'm going to have chromium solid going to chromium 3 plus our 3 electrons. And then just so I don't have to keep scrolling, I'm going to write those numbers here. So my cell potential for my oxidation is going to be a positive 0.74 volts. And then my cathode, that's my reduction half reaction. And that was our tin 2 plus 2 electrons going to tin solid. And its number, negative 0.14 volts. So that was A. Our shorthand notation, forgot B first. Actually, I'm gonna move some stuff over here. I should have planned this a little bit better, but I'm gonna do B here. So I just wanna line my arrows up. It's just easier for me when I add stuff, not to goof stuff up. So B, we need to add these guys together. So we've already balanced kind of in our steps for balancing reactions using the half reaction method. The first few steps are done, right? It's already balanced for atoms. We've already balanced charge by adding electrons. So the only thing we have left to do is to get our electron count the same and then add them together. Because I have 3 electrons here and 2 electrons here, 6 is my magic number. So I'm going to multiply the top half reaction by 2. So I'm going to have 2 chromium solid, 2 chromium 3 plus, and then I'm going to have 6 electrons. I'm going to multiply the bottom equation by 3. So 3 tin, 6 electrons, and then 3 tin solid. So 3 tin 2 plus. And then we'll add those together. And I will get 3 tin 2 plus 2 chromium solid. Our electrons cancel out, going to 2 chromium 3 plus 3 tin solid. And again, it doesn't matter the order that you write them in. If you wanted to write, this first, so you'd have these two things swapped, same here, it doesn't matter. As long as all of the reactants are on the reactant side and the products are on the product side, you're good. So my answer to part B. C wanted us to write our shorthand notation. So remember, when we write our shorthand notation, we're always going to do the reaction at the anode first. We're going to have a single vertical line if I have different states, reactants first, product second, salt bridge symbol, and then the cathode on the other side. Same sort of idea, reactants first, product second, single vertical line between different states of matter. So my anode, right, that's this. You don't actually have to put the 2's when you're writing the shorthand notation. We can just use chromium instead of 2 chromium. So I'm going to have chromium solid. The next thing I'm going to write is chromium that's in aqueous solution, so a different phase. So we do put that vertical line between them. And then my salt bridge symbol. Cathode comes next. Again, you don't need to write the coefficients. So I'm going to have tin 2 plus, which is in aqueous solution. Not chromium. And then tin solid is going to come next because those are different phases. I needed that single vertical line between them. I don't have to worry about adding platinum or anything because I do have 2 solids. So I will have electrodes for both. Part D. Part D wants us to calculate our cell potential. That's just adding those two together. And again, we do want that to be a positive answer. If it comes out negative, you goofed up previously. So I'm going to take 0.74 volts, and then I'm going to add to that or subtract, however you want to do it, a negative 0.14 volts. Which comes out to be 0.60 volts. So 2 digits after the decimal point, 2 digits after the decimal point. I want 2 digits after my decimal point. And where are we? E. So E, we do need an equation. This is on the back of your periodic table on your equation sheet, sorry. So I have my free energy change is equal to negative N, F is the Faraday constant, and then my cell potential. And then our constant was 96,500 joules per volt. Times moles of electrons, sorry. I know that that looks like mole with a little negative sign. It's actually mole, M-O-L, which is the abbreviation for mole, and then a space, and then moles of electrons. Sorry, that looks so weird. So we can just plug everything in. We have everything we need already. My cell potential is this number that we just calculated. F is my Faraday constant, and then N is the number of moles of electrons we're transferring, which is 6, right? We do have that number when we balanced it from above. If I didn't actually ask you to balance the equation and you were just starting with this, you would have to get those electron counts equal, right? The number of electrons lost has to equal the number of electrons gained. So I can't be, losing 2 from one and gaining 3 on the other, or vice versa. They have to be the same number. So you would have to go through and get those electron counts equal. So it is going to be 6. So my free energy change, I just wanted to use a different color for the formula than the work, is negative 6 moles of electrons multiplied by 96,500 joules, volts, moles of electrons. Sometimes I abbreviate moles, sometimes I don't. 0.60 volts. And then units. Moles of electrons are canceling, volts are canceling. We're left with joules, which is a unit for energy, so things are looking good. I'm gonna grab my calculator here. And I'm just gonna double check it one more time. And I got a big number. We'll worry about sig figs here and rounding in a second. So it's negative 347,400. And this is in joules right now. I am going to convert it to kilojoules. And then also we want 2 significant digits in our answer. So I'm going to convert to kilojoules and then also round to my 2 significant digits. So to convert to kilojoules, we're going to divide it by 1,000, essentially move our decimal place over 3 places. So I'm going to have a negative 350 kilojoules, right? If we look at this, I'd have a negative 347 kilojoules, but then that's 3 significant digits. So this 7 is going to round that 4 up to a 5. The other way you could write it is you could put it in scientific notation, and that would work too. So either one of those. Just be careful with those zeros, right? If there isn't a decimal point here, then this 0 is not significant. When I put it in scientific notation, I do have a decimal point. So if I kept that 0 there, it's now 3 significant digits. So do be careful with those trailing zeros. So one more part, and that's drawing our galvanic cell. So this is part F. So we're going to have our 2 half cells. I'm going to have my electrodes in here. They're getting kind of messy. We're going to connect them with our wire. And then I'm going to do the anode on the left again, and I'm just going to copy these down so I don't have to scroll up so much. So my anode is going to be on this side. Again, for this one, you could put them on either side. My anode is going to be my negative electrode. My cathode is going to be my positive electrode. And then remember, my anode is my, I guess we have it labeled here still, but my anode is going to be my oxidation. So this is going to be chromium solid. And then I have chromium ions, 3+ in solution. Here I have tin solid, and then I have tin 2+ in solution. And then electrons, right, are going from chromium, right, I'm producing them there, to tin, that's where I am consuming them. So my electrons are moving in this direction. We do need to add a salt bridge. I didn't tell you what to put in there, so I'm going to use sodium sulfate again. So sodium ions, remember the positive ones are going towards our cathode, and then my sulfate, my anion, is going towards the anode. So my galvanic cell for this reaction.